Now we want to calculate the power dissipated through each of these LEDs when the circuits are complete. At the moment they're not complete, the battery is not connected across. But when the LEDs shine, what is the power dissipated through each of these LEDs? Remember that power is the rate at which energy is transferred, energy per time. How much electrical energy gets converted into light each second. And the more light comes out each second, the brighter the LED will be. Power is measured in the unit watts, which is the same thing as a joule per second. How do we calculate power in the context of electricity? One way to do so is to multiply the potential difference across the device, across the LED, by the current strength through the LED. And that is what we're going to do to calculate the power dissipated by each LED. So we are going to use this multimeter as a voltmeter, and we're going to connect the circuits so that the LEDs shine. And then we need to measure the voltage across each of the LEDs. And that information we're going to write in this column over here. Then we also need to measure the current strength through the LED. For that we need an ammeter. We're going to use this multimeter as an ammeter. So we need to connect it in series within the circuits. So we're going to complete the circuit using the ammeter, and then that will give us the reading of the current strength in the main part of the circuit for each circuit. Now for circuits 1 to 3, that is also the current strength that is through the LED. So there's no problem there. By measuring the current strength in the main part of the circuit, we will also be measuring the current strength through the LED. However, we will just have to be careful for circuit 4, because in circuit 4, when we measure the current in the main part of the circuit, that's where the ammeter will be placed, that is not the current strength that is actually going to pass through the LED. Why? Because at the branch here, the current will split. And this one here is I main, and the current through this one we could call I1, and the current strength through this LED, I2. And we know that in a parallel circuit, I main equals I1 plus I2. So not all of the current that we measure will actually go through the LED. So we'll just have to be careful with that. So this is going to be our voltmeter. Let's set it on the voltage maximum 20 volt setting. And it has to be in parallel across the LED in each case. So I'm going to use some crocodile clips to help me. I'm going to use this red crocodile clip on the red probe, on the positive probe. And I'm going to connect that over here to the LED, to the positive side of the LED. And then this is the negative probe of the voltmeter. So if the circuit was connected, then this would be measuring the voltage across the LED. And let's use a crocodile clip there as well to hold that in place. So we have the voltmeter in parallel across that LED. Now we need the ammeter here, which we set at 20 milliamperes maximum. An ammeter must always be connected in series. I'm just going to connect it straight to the negative terminal of the battery. And then the positive terminal of the ammeter needs to complete the circuit. And I'm going to use a crocodile clip. I'm going to connect it there. So as soon as we then connect the positive terminal of the battery over here, we will have a complete circuit. So notice we have a complete circuit from the positive terminal of the battery through the LED. The current flows through the resistor and then through the ammeter and then around back into the battery, negative terminal of the battery. And we have our two readings. This one's voltage, that one's current strength. So we see that the voltage across the LED in circuit 1 is 2,06 volts. And the current strength through the main part of the circuit, which is also through the LED, is 7,41 milliamperes, which is 7,41 times 10 to the power minus 3 amperes. And we can see the unit there is in amperes. Now we move our connections down to circuit 2. Let's make sure we transfer everything. So now we have the voltmeter across the LED in circuit 2, and the current strength will be completing the circuit. as long as I touch the positive terminal over here. So for circuit 2, the potential difference across the LED is 1,78 volts. The current strength through the LED, 0,36 milliamperes, which is equal to 0,36 times 10 to the power minus 3 amperes. Now we transfer our connections to circuit 3. The voltmeter connected in parallel across the LED there. The ammeter completing the circuit as soon as I also touch the positive terminal over there. For circuit 3 we have voltage across the LED of 1,82 volts and current strength 0,71, and that's in milliamperes. We multiply that by 10 to the power minus 3 to get amperes. Our last circuit, again, we transfer the connections. It doesn't actually matter to which of these loose tails we connect the crocodile clips because they are all connected to one another at this point. So you could also connect this onto the screw and the same this one onto the screw as long as the voltmeter is connected in parallel across the LED. And then we connect the ammeter there so that we complete the circuit by touching the positive terminal to that screw there. And we have a voltage across the LED of 1,75 volts. Now we have to be careful. We are measuring 0,36 milliamperes, but that is through the main part of the circuit here. It's not through the branch, the LED. So we have 0,36 milliamperes flowing in the main part of the circuit. And we know that across these components, across the parallel connection, we have 1,75 volts. So from that we can calculate what the current strength is through the 10K resistor and subtract that from the current through the main part of the circuit because the remainder goes through the LED. In other words, this here is I main, 0,36 milliamperes, and I main is equal to the current strength that goes through the 10K resistor plus the current strength that goes through the LED. So if we want to know only the current strength that goes through the LED, we just rearrange, do some algebra, and it tells us that we must take I main, which we know is 0,36 milliamperes, and we must subtract away I through the 10K. So how do we get the current strength through the 10K? We know that current strength is equal to potential difference over resistance. The potential difference is 1,75 volt. The resistance is 10K. When we divide volts by kiloohms, our answer is in milliamperes. If we divide volts by ohms, our answer is in amperes. So let's get our answer in milliamperes. 1.75 divided by 10, we don't even need a calculator. Of course, it is 0,175 milliamperes. So that is the current strength through the 10K resistor. So we subtract that from the current flowing through the main part of the circuit, and our answer is 0,185 milliamperes. So we know that 0,185 milliamperes travels through the LED. So we have 0,36 milliamperes in the main part of the circuit, and that splits. It doesn't split completely equally, but almost equally. A bit more goes through the LED than through the 10K resistor. But when you add these two up, you will get this value because that value has just split up into the two branches. So we found what we needed to find, the current strength through the LED, 0,185 milliamperes. 0,185 milliamperes is 0,185 times 10 to the power minus 3 amperes. So this is the current strength through the LED, not through the main part of the circuit, through the LED. Now we need to multiply these values with one another to find the power dissipated through the LED in each case. So now we need to do these calculations. 2.06 multiplied by 7.41. Now we need times 10 to the power minus 3. We find it there on this particular calculator in orange, meaning that to access it we must press second function and then that button. So for this particular calculator, times 10 to the power something is got by times second function log, and you can see that that's brought in times 10 to the power something, and then we use this sign, negative minus 3 equals, and that gives us our answer. I'm not going to write it in scientific notation on purpose so that it's easier to compare the values. 0,015 watts. Clear the calculator. 1.78 multiplied by 0.36 times second function log for times 10 to the power, this negative sign, 3 equals. Again, normally one would write this in scientific notation as 6,4 times 10 to the power minus 4. But for easier comparison, I want to write it just in normal notation over here, 0,00064. Clear the calculator. 1.82 multiplied by 0.71 times 10 to the power negative 3 equals 0,0013 watts. 1.75 multiplied by 0.185 multiplied by 10 to the power negative 3 equals 0,00032. So what do we see here? The highest number here is 0,015. And that was the circuit where the LED shone the brightest. Circuit 3 had the second highest wattage reading, and the LED was second brightest in circuit 3. This number is the third greatest, and this number is the least. And indeed, that is what we saw. Circuit 4 was the dimmest of all. So what we've seen is that the power dissipated through the LED corresponds to the brightness of the LED. And that is not surprising because power means the rate at which energy is transferred. So it's the rate at which electrical energy is changed into light energy in the LED and transferred to the surroundings. So the greater that rate, the brighter the LED.